Hi all, this is part 8 of module 1 and today we will discuss about quantum well in detail. First of all, I will try to refresh the basics of potential wells. Consider an interesting example. Suppose I am going to place a ball at the top of the hill, here. And when I release the ball, it will fall freely through this way, okay. Suppose there is a big hole and it is here, okay. And when the ball reaches here, it will be trapped inside this hole and it cannot escape because there is enough barrier to restrict the free fall. And if the barrier is very small, the ball can somehow rise to exit the hole. But here, the hole's depth is sufficient enough to restrict the free fall of the ball. Now, in our case, consider two different semiconductors. Suppose it is gas and gas, aluminum gallium arsenide and gallium arsenide. In short, I will say gas and gas. Gas is wide band gap semiconductor when it is compared to gallium arsenide. And as the percentage of aluminum increases, gas will become more wider and wider. Check the figure. Here gas is sandwiched between two gas layers and gas is nanometer size. So this is a quantum well structure. And since the dimension of gas across this axis is restricted, the electron movement also confined. The electron movement across this direction, it is confined. Now check the quantum well formed here. Eg1 is the energy band gap of gas and Eg2 is the energy band gap of gas. Since there is energy difference, a well is formed here. There is sudden change from gas to gas. So the potential suddenly drops very sharply. Okay, that's why it is a square well. Electrons from gas will be trapped inside this well. The electrons can withstand in any one of the energy levels within the well. Since gas is in nanometer size, the energy states is discrete. We know that in bulk semiconductors, energy states are continuous in nature. In quantum wells or in nanoparticles, energy levels are discrete with quantum number 1, 2, 3, etc. And most of the electrons will occupy the lowest energy levels. And one more thing, since the dimension across this axis is restricted, the electron movement is also confined through this direction. And the trapped electrons cannot climb the barrier in normal case because the potential difference is huge. Otherwise, you need to apply the external potential. Okay. In practical way, the barrier is finite and this is called finite square quantum well. And here, the region 1 and 3, they are wider band gap materials and region 2 is a lower band gap material. Potential in region 1 and 3 be V0 and let the width of this well be small a. Inside the well, the potential is 0 and from the center point 0, here it is taken as a by 2 and here it is minus a by 2. And the potential can be represented as outside the well V0 and inside the well potential is 0. And now we can recall the Schrodinger wave equation. It is shown here. So outside the well, the potential is V0. Okay, so the equation will become d square over dx square of psi 1 plus 2m divided by h bar square. Energy minus outside the well, it is V0 into psi, which is equal to 0. Psi is the wave function. Then inside the well, the potential is taken as 0. So the equation will become d square psi 2 over dx square plus 2m over h bar square multiplied with energy into wave function, which will be equal to 0. And using boundary conditions, you can solve these equations. Anyway, the solution leads to various possible energy levels and wave functions inside the well. And the possible energy levels are n is equal to 1, n is equal to 2 and n is equal to 3. And the wave functions psi is also shown here. At n is equal to 1, there is one peak, and at n is equal to 2, there are two half waves. One more half wave is added, and at n is equal to 3, there are three peaks. Okay. And towards the barrier, the wave function is exponentially decreasing. There is the barrier. And now we can note down the features of finite square quantum well. So we can observe that the energy of particles or electrons here inside the well is discrete energy levels. When it becomes nano size, the energy levels will become discrete. In bulk semiconductors, it is continuous. And the electrons are free to move outside the well. Inside the well, the movement is restricted. So outside the well, the electrons can move freely. It can move freely if the energy is greater than V naught. And one main thing, if you study the wave function, it penetrates through the barrier or through the forbidden region. So still there is small probability to see the electrons outside the well. And this is known as tunneling. It's very important. And we will study the tunneling effect in module 4. And this penetration of electron wave function through the barrier is very small for lower energy state. That is at here. Okay. And next one is parabolic potential well. We know that the potential due to harmonic oscillation is V of x is equal to half kx square. In simple harmonic motion, electrons oscillate under parabolic potential, and the plot of this potential energy is parabolic in shape. So in nanoelectronics, and if we apply magnetic field to quantum well structures, it will produce parabolic potential. And consider this structure: gas, gas, aluminum x percentage, gallium 1 minus x percentage, and arsenide. This means if aluminum is 70%, gallium will be 30%. That is aluminum 0.7, gallium 0.3, and arsenide. When we increase the percentage of aluminum and decrease the percentage of gallium, then the material will become more wider. So here at the interface, when we move from aluminum gallium arsenide to gas, the percentage of aluminum is decreasing. That is, it is linearly decreasing. Therefore, the potential also linearly decreases. When we move from gallium arsenide to aluminum gallium arsenide, percentage of aluminum is increasing and the potential linearly increases. So here the potential well will be parabolic. And back to the Schrodinger wave equation, in parabolic well V is equal to half kx square. Therefore, the equation will become d square psi over dx square plus 2m over h bar square, energy minus V is, the potential is half kx square multiplied with wave function, which is equal to 0. The solution of this equation will give the possible energy levels, that is E suffix n. And n is the quantum number 0, 1, 2, 3, etc. And check the figure. This is the parabolic well, then possible energy levels, and these are the wave functions. And here also the energy is quantized energy levels or energy states. And towards the barrier, the wave function shows the penetration, that's the tunneling of electrons. And next one is triangular wells. We can see these triangular wells in modulation doped heterostructures, that is at the interface of gas materials. Modulation doping means the doping level of aluminum is linearly varying at the interface. Okay. The potential well is shown here, and these wells can be observed in most structures also. And here the potential is linearly increasing, that is V of x is equal to E f x. E is the charge of electron, and F is the uniform electric field, and x is the distance. And beyond this point, the potential is taken as infinity. We can see the energy is also quantized, but here we can see that as the quantum number increases, the energy level difference between two successive levels decreases. So there will be collaboration of the wave functions. As the quantum number increases, one more half cycle is added here, added to the wave functions. Here one half cycle, here it is 2, and here it is 3. And wave function penetrates through the barrier and it is exponentially decreasing towards the barrier. So I will stop here, and these are the very important questions from this session. You can refer it. Okay, thank you.